couple of announcements, kind of. So Friday, come 10 minutes early for a pop quiz. No, for pizza. We decided that both Monday and Wednesday groups will get pizza. Well, partly because you all did really good, and partly because we kind of lost track of points. So we decided we'll have everybody win a pizza lunch. So if you come 10 minutes early, you can serve yourself pizza and we can get started with the lecture. I'm sorry for those of you that said they will not be here on Friday. Okay. Monday group, you did not turn in your Excel sheet. You don't want your 20 points? For the lab, you need to turn in your Excel sheet by end of today. If you don't, you're going to get a 0. This is a gift from me to you. Don't make me give you a 0. Turn in your 20 points Excel sheet. Some of you, maybe 2 of you only turn it in. Okay, Wednesday group, make sure you turn it in by end of the day. We made sure that everybody at least reached towards the end of calculations. Extra credit, don't forget pH non-treatable acidity due today. On Friday, the protein characterization. By 5, if you don't have it done now, you can turn it in by 5 under my office door if I'm not in the office. Some of you really need these points. Okay, lab notebook, last check next week. Make sure you have it ready. If we end up having a review session on Monday, I asked the Wednesday group if all of them can do the Monday review session. We might only have Monday, so please bring your finalized lab notebook with every single experiment, including today's, this week's experiment. Okay, again, these are easy points and kind of a gift from me to you, so why not just get them? Get these points. Okay. All right, let's continue where we left off for vitamins. Just a few recap questions. I want to move a little bit fast so that I can get to minerals today as well. So what are some fat-soluble vitamins? Yes? A, D, E, K, or ERIC. What are the common steps in extracting them? Yes, Claire? Saponification to release them from the fat component. So if you have triglycerides bound with your vitamins, we can saponify triglyceride, solubilize those, and get your vitamin into the organic solvent. Okay, what are some precautions during sample preparation and why for vitamins? Yes, Marissa? Yes, so light and oxygen for some vitamins. Some vitamin like riboflavin is super sensitive to UV. Vitamin A and vitamin C are super sensitive to light and oxygen. Also heat. We want to make sure that we don't expose our certain vitamins that are thermolabile, like vitamin C, to heat during sample preparation. pH consideration, so that we don't induce oxidation under alkaline conditions. So we have to really make sure that we don't alter our vitamin or vitamins before we analyze them. And this, the last one is based on the next method that I want to explain. Vitamin C determination in juices and beverages is usually done by the official method of analysis, which is the dichloroindophenol method. This is a simple titration method where it's based on the reducing power of vitamin C. So you have the dichloroindophenol dye, which in its oxidized form, it has a color, a dark purplish color. However, when it gets reduced, it goes colorless. So your beverage that has ascorbic acid or vitamin C in it you titrate with the colored dye, and every time you add a drop, it will turn colorless because the vitamin C is reducing it, until all vitamin C has been oxidized by the dye. So ascorbic acid reduces the dye, and the dye oxidizes the ascorbic acid. So when all of the ascorbic acid reacted, there's no longer any available reducing agent, any available vitamin C in the reducing form. Then the next drop will turn your sample pink. And you know that this is the end of the titration. And you use the volume of dichloroindophenol to deduce the amount of vitamin C you have in your sample. What do we do if the sample is colored? So if we have really dark colored sample that has vitamin C in it, we won't be able to distinguish, it won't be colorless or pink, really. In this case, you would measure absorption at a particular wavelength, unique for that dye. That's how we do it, if the sample is colored. So this is the reaction. You have the L-ascorbic acid, which is in the reduced form. And then you have the oxidized dye. Well, it's not really red. It's kind of a purplish dark color. And here is the oxidized ascorbic acid, and then the colorless dye once it is reduced. Now, in processed juices, for example, sometimes vitamin C turn into a primary oxidative form. That means you get aldehydoascorbic acid. The aldehydoascorbic acid is the oxidized form of L-ascorbic acid, but it's still biologically available. It's not completely degraded. So mild heating, mild processing might cause the oxidation of L-ascorbic acid into that form, the aldehydoascorbic acid. So if we get a pasteurized juice, you might have some aldehydoascorbic acid in there, orange juice. So this method measures only the L-ascorbic acid. If I want to quantify aldehydoascorbic acid as well, what do I do in the analysis? Think about it. What can I do? What step I need to add in order to be able to measure both forms? It's not too hard. Just think about your chemistry a little bit. What do you do in order to quantify this as well? Very simple.
You just need to reverse that.
Yeah, you reverse it. How do I reverse it? Very good. How do I reverse it? So it is in the oxidized form, so I add a reducing agent. All right? So I get the add the reducing agent. Any aldehydoascorbic acid present in my sample will be reduced to L-ascorbic acid. Then I titrate. Okay? Then I am able to quantify both. If I want to differentiate in my sample how much originally I have L-ascorbic versus aldehydo, I will run the assay with and without reducing agent. Then I will be able to determine each one individually and the total. Another method for vitamin C is the fluorometric method or microfluorometric method. In this case, you actually want to oxidize all ascorbic acid. So L-ascorbic acid is oxidized to aldehydoascorbic acid. And then the oxidized form reacts with phenylene diamine, which will give you a fluorescent that you will measure fluorescence of. This measures both forms because you are converting everything to aldehydoascorbic acid. So it really gives you the total amount of ascorbic acid you have. If you want, again, to distinguish, you can eliminate the oxidation step and just measure right away anything that has been in the L-dehydroascorbic acid form will be detected. Then you oxidize in another experiment, you oxidize all of L-ascorbic, you get the total. Then this way you can also get how much you have L-ascorbic versus L-dehydroascorbic acid. Lastly, thiamine and riboflavin are thermally stable vitamins, and in order to extract, and they're water soluble, so in order to extract them, we use autoclaving with acid. Then these are extracted. Thiamine, we use an enzyme to remove the phosphate group. We hydrolyze the phosphate esters and then clean this up with chromatography and oxidize to thiochrome and then measure fluorescence. Thiochrome fluoresce. So we can measure fluorescence. Riboflavin, we oxidize interfering material that might fluoresce at specific wavelength, and again we measure fluorescence for riboflavin. That's it. That's all you need to know. Move on to minerals. Do I need to save this? Okay. Mineral analysis, which is the last compositional analysis we're going to talk about before moving on to a couple other things. Why is it important to analyze minerals? I'll go with Nico.
You need to list them on the food label.
Nutritional labeling is one important thing, obviously. What's on the nutrition label? Current one. What minerals are on the nutrition label, current ones? Who are talking? Yeah. Potassium, that's the new one, the upcoming one. Jillian? Iron and calcium, and one more. Caitlin? That's vitamins, right? Yeah, but vitamin A and C is correct for vitamins. Sodium, yeah. All right, so what another importance for analyzing minerals is when you fortify with minerals. Here, I'll show that. When we fortify with minerals versus naturally present. If we fortify, oftentimes you see a whole list of minerals on your nutrition label, even though they are not the ones that are currently you're obligated to put it on the label. So, so that's for fortification. For processing effects, so let's say if you're using refined flour, you are, by FDA, you are supposed to enrich your flour with what minerals you have lost, especially iron, because most of the minerals are located in the bran portion. So when you are using refined flour, you are reducing the nutritional value of that flour by removing a lot of the minerals. So enrichment is another is a way to counter that, and you need to make sure by measuring the minerals that you have reached the level that it was originally before processing. Sometimes minerals are added for their functionality. So we add salt for certain texture and flavor component in baked products. So you want to make sure that you don't exceed a certain amount of salt that becomes really not very healthy, or you don't want to reach a really high level of sodium anyway. And sometimes you fortify with calcium to enhance the gelling properties. So sometimes you add calcium to milk to make cheese. Even though that milk has calcium, you even add more calcium to enhance the gelling of the cheese or the curd formation. So you increase the amount of calcium that you actually have naturally present. Also, calcium is added to enhance the gelling properties of soy. So in tofu, for example, adding calcium is really common to enhance the gelling and formation of tofu. Water quality, if you were doing the project and if your product had water as an ingredient, and if you don't put testing minerals in water, that is, you lose points. But you're not doing that. But anyway, measuring water quality in terms of the minerals, if you have heard the term hard water versus soft water. So hard water meaning water really high in minerals, especially calcium and magnesium. So that has a negative impact on some processed food. For example, if you're making beverages and your beverage needs to be clear and you use hard water, it causes cloudiness. Or if you're making pickles and then you use hard water, and then your pickles soften because of the amount of minerals in the water will drive water out of your pickle. Then it will wilt. So the classification of minerals, which is really FYI in this case, macro elements, that means minerals needed in amounts 100 milligrams or higher daily versus trace elements that are needed in micrograms per day. And then of course the toxic elements, we want to make sure that we don't have toxic elements in our water or food. So we measure for toxic elements such as lead, mercury, cadmium, or aluminum. Some, I think, was it wild rice, the breakout of arsenic was an issue? Is it wild rice or rice in general that we had a couple of years ago? But there was a problem with arsenic element or mineral in rice present at toxic amount. Sometimes even like fluoride, for example, which is required in high amount, it becomes toxic. Okay. So analytical methods, we already talked about atomic absorption and inductively coupled plasma atomic emission spectroscopy, which are both of them commonly used for measuring mineral content, especially when we are determining several minerals for large amount of samples. But if we have few samples and one or two minerals we are interested in determining, sodium or calcium or phosphorus in few samples, we have other methods of doing that if we don't have AA in our lab or ICP and we don't really have a lot of samples to handle. So these methods can be titration methods, colorimetric method, or ion selective electrodes. So pretty simple methods for mineral analysis. And sample preparation consideration depends on the nature of the analysis. If these are titration methods, oftentimes you don't need to ash your sample. You don't need to remove the carbonic matter. Whereas if we're determining minerals, obviously using atomic absorption or emission, colorimetric method, or ion selective electrode, these three methods require in most cases that you ash the sample and remove the organic matter. So some consideration in sample preparation. What do you think you want to watch out for when you're doing mineral analysis and preparing samples for mineral analysis? What's the first thing you want to make sure you avoid or account for? We kind of talked about that when we were talking about atomic absorption and atomic emission. Yes, Ali?
Like minerals on glassware?
Yes, mineral contamination. Alex and Axel? Good. but yeah, but in this case, if we're doing something different than AA and ICP or ashing, we don't really worry about that, but that's definitely an important consideration. So basically, possible contamination is a big one, and usually we run a blank, or we make sure our reagent or our glassware is clean. And also contamination from when you mill your sample. If you use a mill that has some metallic form in it, it might cause contamination. One way of solving the problem, other than making sure we wash our glassware, is running a blank to account from any contaminations from reagents. Interferences with the analyses could come from pH that might cause ionization. Excuse me, temperature might cause interactions and complexation. Sample matrix that might cause interferences, and reagents that we're using in the assay. In this case, we try to prepare standards with similar sample conditions to account for that. One way we talked about in spectroscopy is the standard addition method. So you want to review that. So I'm going to write down a note for standard addition method. It would be good to review it here. Okay. So titration, it's very common for testing water quality or the minerals in water. So these up here are test strips. They're called aqua check test strips. They are very commonly used to just qualitatively determine whether you have hard water or really high mineral content in your water. Very quickly, and it's based on the titration method that I'm going to explain here, which is EDTA complexometric titration. So EDTA is a chemical that binds minerals. So we use this complexometric characteristic to determine the quantity of calcium or magnesium in water. So what happens here, you get your water, you put a metal ion indicator in there, which will react with the mineral, calcium or magnesium. And it changes color from blue to pink. So once it binds a mineral or the calcium or magnesium, it will change color. Then we titrate with EDTA. The EDTA has stronger affinity to the calcium or magnesium than the indicator. So here indicator has less affinity to the ion than EDTA. So that's what the principle of the method is based upon, the affinity of EDTA to the calcium or magnesium compared to an indicator. It's really pH dependent because you want to make sure that the EDTA is not protonated. That means it has sites to interact with your positive metallic form of your elements, of your minerals. So we usually use a pH that is high enough, 10 to 11, to make sure that all the EDTA sites are negatively charged, not protonated, and can interact with the positively charged calcium or magnesium. So your indicator is turned pink because it's bound to the ion, and then you titrate with EDTA, and every time you drop in EDTA, the EDTA is displacing the mineral from the indicator. So it's taking it away from the indicator. It's binding with it until all minerals or all calcium ions are bound to EDTA. So when the next drop of EDTA goes in and takes the last ion out of the indicator, the color changes from pink back to blue. That means there was no more calcium or magnesium in your sample, and then you use the titration volume to determine the amount of calcium or magnesium in your sample. Mole titration is the most common titration method used for salt quantification. So it's very easy and simple, another titration. And when you're measuring salt, that means you're measuring NaCl mostly. So if you have chloride in there and you react it with silver, you form silver chloride. In the presence of indicator, the chromate indicator, the last drop, so you're titrating with silver ion or silver nitrate, the last drop of silver nitrate, there's no more chloride to react with, will react with the indicator and give you orange precipitate. So it is a forward titration, meaning the number of moles of silver nitrite at equilibrium equal number of moles of chloride. So however how many moles of silver nitrite I've used, I can determine the number of moles of chloride based on the volume of the titrant. Of course, I need the molarity and I need the volume so that I can get the number of moles. Another method to determine salt, NaCl, is the Volar titration. It's backward titration, and in this case you don't titrate directly with silver nitrate. What you do is you add an excess amount of silver nitrate to your sample, a certain amount that is in excess. So chloride will react with silver nitrate, and then there will be remaining silver nitrate in there. Then I titrate with thiocyanate, and then in the presence of iron or ferric ion as an indicator to a red endpoint. So the more salt I have, the less remaining silver nitrate, the less amount of thiocyanate that I need. And that's why we call it backward titration, because here the lower the amount remaining, that means the more chloride you have in your sample. The lower amount of silver remaining means the higher amount of chloride in your sample. So the Quanta chloride titration, which is also a strip, test strip, it's based on more titration, so you can use test strip to actually determine semi-quantitatively the amount of salt in your sample. And it is an AOAC approved method. It's rapid. It has accuracy with plus or minus 10% as a variation, and it really can measure salt concentration between 0.3 and 10%. So it's really often used as a quick quality control measure for salt concentration. Okay. So the recap questions, we'll hold off on them for now. Are they in your packet though? Just want to make sure you have them. Yeah, okay, good. Other than titration, you have the colorimetric method. A common one is usually to determine phosphorus in your sample. So it's based on a chromogen reacting with a mineral to form another colored compound that can be detected using spectrophotometer. So it's pretty simple, but requires ashing so that there is no interferences and you can have a clear solution of minerals. So you're removing all of your carbonic matter. So following Beer's law, you use standards, you determine this, you have a standard curve, and then you can determine phosphorus. The reagent that you use is molybdenate reagent, and it is yellow, gives you a yellow color. The higher the concentration of phosphorus, the more intense the yellow color is. It's a common method for daily phosphorus. Okay. Lastly, you have the ion selective electrodes. That's similar to a pH meter, but instead of measuring the protons, you are measuring different ions: calcium, sodium, chloride, potassium, fluoride. So basically you have an electrode sensitive to that ion instead of the pH or the H electrode. And then difference in electrical potential will be related to the concentration of ions. But definitely you need standard curves. So you prepare standards with different concentration and measure the electric potential of those, and then you can get a calibration curve and then determine the quantity of your ion. Some consideration. Because it's an electrode, it can be sensitive to the total ionic activity in your samples and standards. So therefore, it's very important that the entire ionic activity of your samples should be similar between samples and standards. If the samples have different ionic activity than the standards, then everything is messed up. We can have interfering ions that can lead to 10% errors. Sensitivity is pretty low, which is good, up to 10 to the negative 6 molar. And however, a disadvantage is at low concentration, it might take a long time to give a stable and reliable reading. These are some applications: salt and nitrate in processed food, meat; calcium in milk; salt in butter and cheese; potassium and sodium levels in wine. Now for the remainder of the time, let's work on some calculations. So pull out a piece of paper for +2, and let's take some time thinking about this. It could be a question on the final. So I really need you to actively think about this. at equilibrium, number of moles of remaining silver nitride equal number of moles of the titration volume, the titrant, sodium cythionate, potassium cythionate, and number of moles that reacted with the Cl equal number of moles of Cl. So that, use that as a hint. We're talking about number of moles. From number of moles, you can deduce mass using this if we are talking about C. These two you should be able to know pretty easily. Okay? That's the hint. Anybody got moisture content percentage? No? Yeah? 80%. Anybody got ash percent on dry weight basis? 20%, Riley, thank you. We'll show the math in a minute. I'm going to yell at them. Guys, do you know that we have a class here? I yelled at them. I was very mean. Okay, anybody with an idea of what they're doing for C? Riley has an idea.
I'm curious, why are you using two different types of titration that both test?
We're doing one. We're doing the Volar titration, which involves, first of all, the reaction. It's not a titration. You add an excess amount of silver nitride and react it with the chloride. And then there is a remaining amount of silver that is not reacted. The remaining amount is titrated with potassium cythionate. I don't think anybody in the class, well, except Sam.
This is going to be a guess, honestly. So do you figure out how many moles of the KSCM you're using? And then it looks like it's just a 1-to-1 ratio for how many moles of sulfur is going to be.
You are right on. There's a missing thing in between. Yes, you figure out how many moles of potassium cythionate you've used, and that would be equal to the number of moles of the remaining silver nitrate. So in order to know the number of moles of the entire amount of sodium nitrite, and then you would get number of moles from here, because molarity equals numbers of moles per volume. So you get the number of moles of the total silver, and then you get the number of moles of the remaining silver. The difference will be the amount of silver that reacted with chloride, which is 1-to-1 ratio, gives you the number of moles of chloride. I will solve it on the board. Write it on your piece of paper, but make sure you have a copy of your piece of paper before the final. Okay. So basically what you need is to determine number of moles of cythionate that reacted. And number of moles equal molarity times volume in liters. Okay, because molarity equals numbers of moles over volume. So now you have the molarity, which is 0.1 molar, and the volume in liter is 0.003 liters, sorry. So that gives you 0.0003 moles. Okay? This means the remaining silver nitride is only 0.003 moles. Okay, what was the total that we reacted with the chloride? So number of moles of total silver ion equals volume times the molarity. So 0.1 molar times 0.03 liter equal, and this is molarity, remember, is moles per liter. That's how I got moles here. Liters cancel. All right, so here you have 0.003 moles. So this is the total. This is the remaining silver. This is equal also number of moles of silver, because again it's 1-to-1 reaction. Are we following or not following? If you're not following, tell me, Axel, where to repeat. Should I erase everything and rewrite? All right. All right, I will write it here. I don't know, where was I? Okay, number of moles equal number of moles right at the end of the titration. So that is equal to molarity times volume, because molarity equals numbers of moles per volume. So molarity is 0.1 and volume is 3 milliliters. And I need to convert that to liters. So it is 0.003 equals 0.0003 moles. Because this is moles per liter. And this is liters, so they cancel. So you get moles. So now I know how much silver was remaining. The total silver, I can get the total number of moles of silver ions from this. Volume times molarity. So total number of moles of silver equal molarity times volume again equals 0.1 times the volume in liters 0.03. Again, moles per liter and liter. This will give you 0.03 moles. So I have the total amount of silver and I have the remaining silver. The difference would be the number of moles of silver that reacted with chloride, right? Then number of moles of chloride equals 0.003 minus 0.0003. That's very small number of moles. You know that is equal to moles of reacted with Cl. I know it's getting smaller, but this is moles of silver reacted with Cl. Equal number of moles of chloride equals the difference, which is 0.0027 moles. So now I have the number of moles of chloride, which is equal to number of moles of NaCl, right? Because 1 mole of chloride in 1 mole of NaCl. So this is equal moles of NaCl. So if I want to get the mass so that I'm able to get a percentage, so I know that number of moles equals mass over molecular weight. So if I have the number of moles, which is 0.0027, equal mass, which I'm looking for in grams, and this is moles, and molecular weight is 58.5 grams per mole, then mass equals what? This times this. Anybody's following? 0.158 grams, because moles cancel. And then you get the percentage of salt, because you have 25 grams sample. So it would be percentage equal 0.158 grams in 25 grams times 100. That is, huh? 0.63? I don't remember this number. Ah, yeah, that's right. Haha. Okay. Sorry, I doubted you. Alrighty. Turn in that little piece of paper for +2, but make sure you have it written somewhere else and understood somewhere else. Huh? Yeah. Yeah. So the one we do in class here and the other one here. This is, you did both? That's okay. I'll just put pile here. Today?
Which one is extra? Which one?
The pH is here.
It goes out.
This is pH. Okay. Class pH, huh?
If you could just take a really quick look at this to make sure I was doing
0.83,
that would
I
be
know.
great. So,
But this worked out. This worked out.
I think it would be
Put
like
the
almost exactly
average.
1. Oh,
Yeah.
okay, yeah, hold on, I'll do that. Okay.
Yeah, and then this. No, you have it flipped. Oh,
Yeah,
unboiled.
I had it flipped originally, and
Yeah.
I switched it, yeah.
Okay.
Then,
And
I don't know if my curve is right.
0.25, yeah, that's fine.
Okay.
Good.
Sounds good, thank you.